Hello everybody. In our series of lectures on basic electronics, learning by doing, let us move on to the next. Before we do that, we will perhaps as usual quickly recapitulate what we discussed in our previous lecture. You might recall in our previous lecture we were discussing about some new devices like uni-junction transistor and silicon controlled rectifier or the thyristor. In the last lecture we discussed about the thyristor, the silicon controlled rectifier, which is also called the SCR for short form. We saw the characteristics of the SCR, how the SCR can be triggered by a gate pulse and how it can be used for power control both in the DC as well as in the AC mode, and the DC and the AC characteristics was discussed, and at the end I also showed you a demonstration how in a simple scheme the SCR can be used to control the intensity of a light lamp. The same idea can be extended to control the energy delivered, power delivered to a fan or to any other type of a electrical device. Before I concluded, I also gave a very brief idea about the other two variations of the SCR, namely the triac and the diac. Now in this lecture I want to again present to you another new device, very important device, which I have so far not discussed, that is namely the field effect transistor. So the field effect transistor is a very important development in the history of electronics, and therefore it is important that in a course on basic electronics we should at least have some discussion about the field effect transistor. You might know, if you look at the history of the electronics, we started with vacuum tubes. You can see on the screen we started with vacuum tubes. This is actually a vacuum tube triode. You have plate, grid and the cathode. The filament is anyway a constant factor in all the things for generating the thermionic electrons. Then came the solid state device that we have already seen, the transistor, but it is one form of the transistor which is called the bipolar junction transistor, the NPN or the PNP type of transistor with the collector, base and the emitter. Now what we are going to look or discuss in this lecture is going to be the JFET, the junction field effect transistor, whose symbol is shown here. Again you see it is a 3-terminal device, the drain, the gate and the source. In all the three devices there are certain common features. There is a current which is flowing from plate to the cathode or the collector to the emitter or the drain to the source, but we use the third terminal, the middle terminal, the gate or the grid or the base as the case may be, is used to control this flow of current between the drain and the source or collector emitter or plate cathode. So that way the basic characteristic of the device is the same in all the three cases, that is there is a large current flowing between two terminals and the voltage or the current on the third terminal is used to control the flow of the main current flowing through the two terminals that we talked about. So that is a basic principle, that is why it is called a valve, vacuum tube valve, or in this case transistor, which is an amplifying device, an active device. So what is a field effect transistor? The field effect transistor is basically again a semiconductor device, solid state device, which depends for its operation on the control of current using electric field that is applied between the gate and the source. So you have three terminal, drain, source and the gate. So by controlling the voltage between the gate and the source, you will be able to control the current between the drain and the source. That is what basic function of the FET is. There are two types of field effect transistor that we normally come across. One is called the junction field effect transistor, which is almost rarely used these days in the laboratory, more for basic understanding, and the other one is the more popular version, which is called the insulated gate field effect transistor, the IGFET. The IGFET is basically a FET, which is a modification of the junction field of a transistor, but this Ig FET is the one which is responsible for the other things that you have already come across, like the MOS, the metal oxide semiconductor field effect transistor, the MOSFET, or the CMOS, the complementary symmetry metal oxide semiconductor field effect transistor. These are the variations of the Ig FET, insulated gate FET, and they are the ones which basically revolutionized the field of electronics, because these field effect transistor and the metal oxide semiconductor transistors can be fabricated on planar technology, on one single plane of a semiconductor silicon wafer, and therefore you can put more density of those active devices per square inch, and that brought in the revolution that you see all around in electronics, basically in the integrated circuit electronics. So JFET and field effect transistor in general is a very important step in the development of electronics. So it is again a 3-terminal semiconductor device in which current conduction is by one type of carrier, that is, it is either by electrons or by holes. It is a unipolar device, that is what we call it. You should compare it in with the BJT, the bipolar junction transistor. In a bipolar junction transistor, during the operation you would find there will always be two types of carriers at any time, the majority carriers and the minority carriers. The majority and the minority carriers can be the electrons and the holes in whatever combination. It depends on whether the device is an NPN transistor or a PNP transistor. So you can have two types of charge carriers contributing to the current, total current, whereas in the field effect transistor it is a unipolar device. That means the current that is caused or being controlled is basically due to either electrons or holes. How is it? We will just discuss in a moment. So this movement of the current is controlled in this case by the electric field between the gate electrode and the channel or the source. So this is a field effect. What is electric field? Electric field is electric voltage divided by the distance. If I have something like a capacitor plate, if I apply a large voltage, the electric field is a voltage divided by the separation distance d between the two electrodes. So here also it is a field which is responsible in controlling the flow of current. You should again compare this with the BJT, bipolar junction transistor, which is basically a current operated device, current controlled device. Junction field effect transistor is a voltage controlled device, and it is very similar in that sense to a vacuum tube triode. In a vacuum tube triode also, you know, it is just vacuum inside, you have a plate and you have a cathode, in between you have a grid which is normally positioned very close to the cathode. Therefore, when the electrons are emitted from the cathode by using the filaments by thermionic emission, they will start going towards the plate when the plate is more positive. Now to control the flow of electron, you apply a voltage on the grid, small voltage, because the grid is very close to the cathode. The field due to this voltage will be very large compared to the field due to the voltage kept on the plate, because the grid is very close to the cathode, the distance is very small. Distance comes in the denominator for the field, F is equal to V by D, and therefore the field corresponding to the grid will be very high, and so it will be able to control the flow of electron between the cathode and the plate very conveniently, and therefore that is also a field controlled device or a voltage controlled device, similar to the junction field effect transistor, where again the control of the current is by the electric field rather than the current. In which case, in the case of BJT, bipolar junction transistor, you know, it is a base current which is basically controlling the emitter current or the collector current in the common emitter mode you would have seen, and therefore it is basically a current control device, and the JFET is a voltage control device. That is a bipolar device, this is a unipolar device. So there are a lot of advantages and disadvantages of the devices, so one has to choose the proper device for a particular application. Okay. So this is what I have actually listed here in this slide. The FET differs from the bipolar junction transistor in the following important characteristic. The operation depends upon the flow of only majority carriers. It is therefore a unipolar device. It is simpler to fabricate and occupy less space in integrated form. This is a very important form technologically, and therefore it provided the giant leap we require in the field of integrated electronics, IC electronics. The most other important characteristic of the JFET is that the input junction is reverse biased. In the case of transistor, the base emitter junction will have to be forward biased for the transistor to conduct, and all the amplifiers that we designed using these transistors, you would find they will always try to forward bias the base emitter junction, and the forward bias base emitter junction will be a low resistance device. Input resistance will be lower, and therefore it is a low resistance at the amplifier input, as against what ideally we would require for a good voltage amplifier will be a high input impedance. Therefore transistors are not really very good for voltage amplification in that sense. Whereas if you take the JFET, the input junction is to be reverse biased between the gate and the source. Because it is reverse biased, the input impedance of an amplifier made out of JFET is also very high, and therefore that characteristics also is very important in the design of different circuits. So there are many operational amplifiers that we talked about. You would find there will be FET input operational amplifiers. So they will try to introduce in the differential amplifier that you introduce at the beginning, at the input stage, you would try to include a JFET rather than a BJT, so that you will have very large input impedance, and that is a very important characteristic that will bring down the input bias current and several other good characteristics of the operational amplifier. Therefore using JFET will be prompted by large input impedance that it provides at the input stage. It is less noisy than bipolar transistor, and it exhibits no offset voltage at 0 drain current and makes excellent signal chopper. These are more advanced applications, but let us try to see the circuit symbol of the JFET. There are two types again, just as you have in BJT, you can have NPN transistor or a PNP transistor. In the same way you can have two transistors here, one is called the N channel field effect transistor, the other is called the P channel field effect transistor. The circuit symbol, the difference is only in terms of the arrow, just as you have in the case of transistor. Even in the case of BJT, bipolar junction transistor, the emitter will have an arrow which will be in opposite directions for the PNP and the NPN. Similarly here the N channel and P channel will be shown by the direction of the arrow that you see on the screen. You must also compare it with the symbol of an UJT, unijunction transistor, that we already talked about. You would remember in the case of unijunction transistor, the base, the gate terminal will have a break here, it will have a slant here. In the circuit that you see here, there will be a slant here, that if the same arrow is bent here, and then it becomes a UJT, if it is straight then it becomes a FET. So you should remember the difference in the circuit symbols of these devices. Now basically what is the field effect transistor? It is nothing but a simple silicon block. You see here on the screen, you have a silicon block here, and you have, this is a N type or a P type. Let us assume that this is N type. Then if it is an N type, that is what it is, then you find there are two regions here which are called P plus type gate. P plus means heavily doped P type. So the difference between this and this UJT again is the UJT, the P type region is a very small region, almost near the middle of this N channel, whereas in this case it will be reasonably over a region, and more importantly this P type will be all through like a belt around the silicon block that I consider. So you will have all around a P region, and that provides the gate region. So that is what is shown in this picture. By connecting the two shaded white shaded area, I have connected them together and I call that as the gate, that is a gate terminal, and one end of the block is called the drain, the other end is called the source, between which I will have to apply a large voltage which is called the drain source voltage. So you have three terminals, the drain, the other end is the source of the n type block, and you have the in between the something like a belt region which is called the gate region. Okay, now what is going to happen? Let us understand the basic characteristic of the field effect transistor. So I have shown here the same in the circuit. You have a block of n type semiconductor, let us assume, and you have the two gate regions on either side. These black things are the electrodes, metal electrodes for contact. So the drain is connected to a power supply which is variable VDD, and the source is grounded. So this voltage supply is between the drain and the source, and you also have a voltmeter connected between the drain and the source, and here there is also a connection between the gate and the source. It is actually shorted, there is no voltage here. So the VGS, the voltage between the gate and the source, is equal to 0. The VDS is variable with this battery here that we have. You can measure the voltage, and the source is common, and that is grounded. So this is the configuration now. Now if I keep increasing this voltage, and if I put a current meter here and measure the current, what do you think will happen? Because this is just a simple n type semiconductor, it can be equated to a simple resistor for all practical purposes. So when I increase the voltage, for some limits you would find the current will keep increasing because it is just simply ohmic. So if I draw a graph between VDS and IDS, VDS is a voltage between the drain and the source, IDS is a current that is generated between the drain and the source. So if I monitor that, you will have a beautiful straight line which is nothing but simple Ohm's law, but this straight line will come up to certain value of the voltage. Beyond that, what is going to happen? Now you should remember this resistor, if you measure the voltage at the drain point, it will be the applied voltage. If you measure at this point, it is a 0 at this, because it is the source. In between you have a resistor. So if I measure at any point in between, the voltage at that point will be a fraction of the total. It becomes a potential divider. The region on the top and the region at the bottom, it becomes a R1 and R2. Therefore the center you will have a fraction of the total voltage applied only. So you find at various points along the channel, you find the voltage is different. At this point it is high, it is slightly less, still less, still less, still less. So it keeps on coming down, and therefore what is the effect of that? You find because this is connected to ground, the gate is connected to ground, the drain is connected to plus of the battery, therefore on the N side there is a plus voltage, on the P side there is 0. Therefore you find N side is more positive than the P side, the gate, and therefore there is reverse bias. There is a reverse bias, but more importantly this reverse bias is not a constant. It has got some value very close to the top, it has got a higher value because the voltage there is more, and as I come down there is a drop along the channel because the channel is something like a resistor, and therefore at different points along the channel the voltage is different, less and less, and therefore the reverse bias on between the gate and the channel is also different at different points. It is maximum at the top and minimum at the bottom. What is the effect of this? The effect of this is, as I keep increasing the VDS voltage, you would find the depletion region produced on the N type will no more be perfect rectangle or something like it will have a wedge shape. You would find the depletion region will be proportional to the reverse voltage, it will be more on this side, the thickness of the depletion region more at this point and will be less at the bottom. Therefore slowly you will find at the top the region available for conduction of the electron, the resistance, that will be much less compared to the bottom. So there is some wedge shape thing. Because of this the current will be constricted while it is flowing through this channel, and therefore you would find the characteristic will show a bend. As I keep increasing the voltage beyond certain critical voltage, threshold voltage, you would find it slowly bend, and finally when this becomes very large, when the reverse bias becomes very large, when the two depletion layers come together almost, you would find very small region for the electrons to flow, and therefore you cannot push the electrons still further because the electrons are negatively charged, therefore they repel each other. So, there is a repulsive force from inside the electrons flowing in the channel, and there is a crowding effect due to the channel depletion layer keeping increasing in width. So, you would find there will be an equilibrium at some stage due to the external pressure and the internal pressure, there will be an equilibrium. Once the equilibrium is reached, no effect of the voltage will be felt, and therefore the current will become a constant. You cannot increase it or decrease it, it will come to a saturation. So, this point is what we call the pinch off voltage. Again I have shown it in the next picture where almost we are at the pinch off. So, then the current becomes almost constant. This current we call IDSS. When the gate source voltage is 0, what is the maximum current, saturation current that I achieve between the drain and source is what I call IDSS, and this is corresponding to a condition called the pinch off. I have shown that pinch off condition by equating it to a normal rubber tube in a garden. When you water the plants in the garden, you have a hose, you have a pipe through which water will be flowing, and if I now start squeezing the rubber tube from all sides, you would find you can never make it completely zero flow. The water will always be, there will be small amount of water still will be coming, but it will be a steady flow. That is the maximum pressure that you can apply on the rubber tube. Therefore, you get very small flow, but it is a very constant flow. That is exactly that is why it is called pinch off. The same thing happens in this case. As the depletion layer keep growing on both sides, the channel available for the flow of electrons will become smaller and smaller in area, and ultimately there will be a constant area below which you cannot change anything, and therefore the current also at that time becomes constant, which we call IDSS or the pinch off current. Now, having seen that, now what will we do? We will go back to the circuit, and then we can also connect a power supply between the gate and the source. We have a power supply between the drain and the source, which I call VDD. You can also have a power supply between the gate and source, which is VGG. In the case where I just discussed, I made VGG 0. Then when I keep on increasing VDD from a small value to a large value, initially it goes like a Ohm's law in a straight line, and then it bends, and once the pinch off is reached, it becomes constant saturation current. Now, the moment I have some voltage on the gate with reference to the source, and more importantly look at the polarity of the battery. The gate is connected to the negative terminal and the source is connected to the plus, that means it is reverse bias. This is the P type, this is the N type. So, P type is connected to the negative terminal and the N type source is connected to the positive, and therefore the gate source junction is reverse biased. And if I now put some, let us say -1 volt or -2 volts here, and then go through again from 0 to a large value for VDD, what will happen? You will see what will happen. You could have also guessed almost, you would find for when VGS is some -1 volt, the saturation will be reached even before, because there is already some negative voltage available on the gate, and therefore I have to go to a much lower voltage on the VDD supply before I can reach the pinch off condition, and therefore you find that pinch off or the saturation voltage or the saturation current comes much lower to the IDSS when VGS is equal to -2. When I make it -2, VGS is equal to -2 or -3, these things will become much less as shown in this graph. So, this is the graph corresponding to field effect transistor, and I have put the other graph also here, which is corresponding to the BJT junction transistor. You can immediately recognize this graph. I am sure we have seen these earlier in our lectures. It is a graph between collector emitter voltage VCE to the IC, the collector current. This is the output characteristics as we call. So, you can see the similarity between the two graphs, but the change is here it is for different IB, because it is a current control device. IB is equal to 30, IB is equal to 20, IB is equal to 10, etc. You have got here. Here it is a voltage device, voltage control device. Therefore, you have VGS equal to 0, VG is equal to minus, VGS equal to -2, etc. So, you find otherwise they look almost very similar, but there is very important difference in that, and that is the saturation current here is much more flat, almost horizontal, constant, whereas in the case of transistor you see there is a finite slope. This is due to the base width modulation as we normally call. So you would find the slope of this line is not completely horizontal, it is not perfectly horizontal, but it has got a finite slope, and therefore this is the very important change that you should recognize in the case of the field effect transistor and junction transistor. Okay, having seen that, now I think it is time for us to go and try the characteristics of the field effect transistor on the work table. So you will see the exact circuit, this same circuit I will use, where I have used the field effect transistor. This is BFW10, which is a standard junction field effect transistor available in the market. You have this voltmeter which measures the voltage between the drain and the source VDS, and you have a current meter which is IDS, and this is about 0 to 10 milliamperes or so, and you have a variable power supply which is obtained from a fixed power supply, and on this side again on the gate side you have a variable power supply and a voltmeter VGS. Remember, there is no current meter here because you know the current is going to be very, very small. It is a reverse bias junction. The current through the gate will be very, very small, and therefore we require only three things: the current or the drain source current, the drain source voltage, at the gate source voltage. These are the three parameters. We will try to vary and see how the characteristics come. You should also remember the graph that I showed to you with reference to the characteristics, right. So I want you to see this circuit. This is a FET characteristic circuit. You have the FET, the same circuit I showed you some time back on the slide. You have the variable power supply here, you also have another variable power supply, and you have the voltmeter and the current meter and the voltmeter, all the three here. So now I have used the millivolt source here as the voltage that is to be applied across the gate and the source. Gate source voltage is used here, this source is used for the gate source supply, and I have here in voltage range. Therefore, if I change it 1, 2, 3, 4 etc., it will be -1, -2, -3 etc., because the terminals are properly inverted when I connect it to the FET. This FET you can see here, this is BFW10, it is a very standard FET which is available in the market. It has got 4 leads. Normally transistor has got 3 leads, here we have 4 leads: the drain, source, gate and shield. The shield is actually one terminal which is connected to the top can, therefore we normally ground it, we do not use it. Okay, then this power supply at the back, this is used, this is 9 volts approximately is what I am using it as the VDD, the drain source voltage, and we have got a potentiometer here which I will use to vary that VDD from 0 to high value, and that voltage VDD will be measured by this voltmeter that you see here. This blue voltmeter is going to measure the VDD voltage, VDS to be precise, and this current meter is the one which is going to measure the IDS, the drain source current, for different gate source voltage. There is no other current meter is required because we are going to only vary the gate voltage and measure. Now I have kept it in 0 position, my gate source voltage, and let us now concentrate on the voltmeter and the current meter as I change the VDD, drain source voltage. So you only see the meters. If you now see the meters, I am going to change the voltage. You see the voltage is increasing, and correspondingly it is about 0.1 volt, and correspondingly the current also increasing. You see it is about 1 milliampere, now it is 2 milliamperes, and as I keep on increasing you find it is 4 milliamperes, 5 milliamperes, and it keeps on increasing and it goes beyond 10 milliampere. That means the IDSS is going to be larger than 10 milliamperes. That is what I see here. If I use much larger, maybe 50 milliamperes, I may be able to get about 12 or 15 milliamperes as the IDSS. Now what I am going to do is I am going to change the gate source voltage to 1 volt, -1 volt. Now I kept it at -1 volt. I will again go through the VDSS, the VD voltage, the voltage on the drain source I am going to increase. Now you should see the meters now again. So, if you see the meters, as I increase, you see the current also is increasing slowly. You can see the current increasing. I keep on increasing the voltage. It is about 4 milliampere, now 8, almost I have come to 8 milliampere. I still increase the voltage, but nothing happens. So, the current is constant at 8 milliamperes. Previously it was going, when VGS was 0, it was going beyond 10 milliampere. It is usually around 11 or 12. Now, when I go with minus 1 volt between the gate and source, the current is saturating at 8 milliamperes. Now, I will bring it back to 0 and change the gate source voltage to another value, say minus 2 volts. I keep it at minus 2 volts now. Let me see, again I go through the characteristics and you observe the 2 meters. You observe the 2 meters only. You would find as I increase the voltage, current also increases slowly, much slower than previously now, and you see here almost I have come to 1 volt. Now it is about 3 milliamperes. I still go further. You will find I am not going beyond 4.5 milliamps or so. I have almost come to 9 volts. Again in the meter, if you see the voltmeter, I am around 8.4 volts, but then the current is only 4.5 or something like that. So, you find the current is now saturating much earlier than what it was for minus 1 volt or for 0 volts between the gate and source. So, if I keep on doing it, I will be able to get all the different characteristics corresponding to different values of VGS, voltage between the gate source. So, we saw the characteristics of the field effect transistor, junction field effect transistor, how for different gate source voltages the saturation current comes differently. If I increase the gate source voltage to minus 1, minus 2, the saturation current comes lower values. You have seen that. But one of the greatest advantage of the junction field effect transistor that I already mentioned to you is the capability to make the junction field effect transistor on the same side of the silicon wafer. So, I have shown a picture here now on the screen. You find I have a P substrate and you have a N type semiconductor grown on the P substrate, and you again have one more layer of P here, right, in the way shown on the graph. Then what happens on either side of the P region, here and here, it becomes a source and the drain. You see, this becomes a drain, this becomes a source, and this is the gate. Similarly, on this side, if you see, I have the drain, I have the source, and in between I have the gate. So, if I now side by side I have got two JFET connected together. At the source it is a common drain is there, but the source and the gate are different. So, on the same side I have got two FETs side by side. Like that I can develop number of integrated circuits, especially the field effect transistors in very small regions on the wafer, and then if I try to do also the interconnections and the resistances using N type or P type semiconductor, then in principle on the same side of the silicon wafer I can generate all the parameters, the resistor, the capacitor. Capacitors are very rare, but you can generate capacitors because it is again the diode, reverse bias diode is the usual capacitor that we have. So, you have resistors, you have transistors, and you can interconnections, you can have metal regions, and therefore, the whole circuit can be fabricated within very small regions of few microns in area on the same side of the silicon. That is what we call integrated circuit. So, the whole revolution in electronics due to integrated circuit became possible because of this capability to generate different devices on the same side of the silicon chip. Right. Now, let me go a little further and show it to you the importance of the other variations of the junction field effect transistor. The junction field effect transistor can be used also as an amplifying device, just as the bipolar junction transistor can be used as an amplifier. The JFET can also be used as an amplifier. I have shown a very simple circuit here where it is very similar to a triode amplifier. You have a load resistor RL and you have a coupling capacitor, and if I have a there is a bias here VGS, VGG we call it, the power supply, and if I give an input signal here, this signal will sit on top of this VGG. Therefore, depending upon the amplitude of the signal, the VGG will be modulated. It may be higher when the sine wave is going higher, and it will be lower when the sine wave is going down negative, and therefore, depending upon that, this current between the drain source will also vary according to the signal. Because this current is varying, that current flowing through that RL will make a voltage develop across this, which will also be varying in exactly the same way as the variation of the signal here, and therefore, the output when I now connect it to a loudspeaker or whatever, you would find I will get an amplified signal at the output. Therefore, the basic junction field effect transistor can in principle be used to amplify small signals which are in the order of few millivolts, because the field produced by millivolts is very large, it will control large current flowing between the drain and source, and therefore, it will produce large voltage variation through after the capacitor at the output. That is the basic principle of the amplifier. I will not be going into too many details of these devices. Normally they can be discussed in at length, the variations of the various devices and the characteristics, the biasing mechanism, and the different configurations of amplifiers that can be constructed using all those things. But due to want of time, I am not discussing, because this is basically this is lectures on basic electronics. I do not want to complicate too much by having too many data, too many information. So, you again see this is the basic configuration of the junction field effect transistor. You see almost horizontal lines corresponding to the saturation. Therefore, in principle this can also be used as a current source. Junction field effect transistor can be used as a current source, and if you find the slope of this, it will be very high. That means it is a high impedance device, and your current source is characterized by a large input impedance. Therefore, the current is going to be constant and dependent only on the voltage you apply between the drain and source as well as the gate and source. Now, I want to show you very interesting thing with reference to the amplifier configuration. You see here I have shown two circuits. The circuit on the left is basically making use of a vacuum tube triode of the olden days. You have the coupling capacitor, you have the bleeding resistor RGL as it is called, and you have the cathode bias RK and CK form the cathode bias for providing a bias for the triode, and you have a RP load resistor. Now, this is a simple amplifier configuration using triode, and by the side of it you see another device which is the modern field effect transistor, and you see the exact replica of the circuit, except that the device is different. Here it is vacuum tube, here it is field effect transistor, and the other important thing is this voltage that is applied at the plate will be around 200 250 volts, whereas here it is about 20 volts. So, the voltages have come down. It is a solid state device, the size has become very small, there is no need for any filament, that means there is no need for a separate power supply, and therefore, the circuit has become very simple, small in dimension, and the voltages are also very low. Therefore, the comparison is very interesting to see. Similarly, if I now take another configuration, here what I have is a transistor amplifier. This is again familiar to most of you. This is a voltage divider bias with R1 and R2. You have the collector resistance RC. You take the output between the collector and the VCC. The input is given at the base through the capacitor. So, this is called the emitter bias, the RECE value. So, this is a amplifier constructed using transistor, and on the left side you have the same amplifier constructed using a field effect transistor, except that I removed the BJT and just introduced the FET. Other than that, the circuit looks exactly identical, and therefore, the design of new circuits becomes rather very simple. If you have a triode circuit, all that you do is take out the triode, reduce all the voltages, remove the filament supply, put a field effect transistor effectively, it should in principle work. It is not as simple as that, but in most of the cases you would find it will be reasonably good to try a design like that. In the case of transistor, you still can have the whole circuit retained, remove the transistor bipolar junction transistor and replace with an appropriate field effect transistor. In principle, you should get your things going without any major problem. So, this is a very great advantage with reference to design of circuits using field effect transistor. There are a lot of related materials which I have not discussed reasonably, but then I want to show you at least one important application of field effect transistor. The field effect transistor I already mentioned to you is very important because the input junction is reverse biased. That means the amplifier made out of field effect transistor will have much larger input impedance. Therefore, I want to exploit that concept and build very useful application circuit which you can quickly try in the lab and learn the importance of the field effect transistor. So, I have given you a circuit here which is actually a field effect transistor voltmeter, FET voltmeter. What is that I have here? I have a field effect transistor and I have a set of resistor. If you really look at it, it is something like a bridge, Wheaton's bridge. One arm of the bridge is having the drain source resistance of the field effect transistor. The other arm has got 4.7K and 5K variable 5K in series. The third arm is having 4.7K, the fourth arm is having 3.3K, and I apply a power supply here, and between the middle terminal I have a current meter and a variable resistance in series. Now, at the base of this FET I have the input voltage. What is going to happen? We all know the drain source current will be controlled by the voltage on the gate, or in another way I can say the resistance between the drain source is going to be controlled by the voltage applied here. When this resistance is going to change due to the voltage applied at the gate, this bridge will get, the balance of the bridge will be disturbed, and therefore there will be some finite voltage developed across these 2 points, and that will drive a current through the milliammeter. Therefore, there will be a deflection in the milliammeter proportional to the voltage here. So, this becomes a very convenient way of measuring the external voltage, because it is reverse biased. I can apply a voltage here and correspondingly there will be a current variation here which can be measured by us, and therefore this becomes a very inexpensive FET voltmeter. You might remember an ideal voltmeter should have a very large input impedance. As a matter of fact, you all would have studied how to convert a galvanometer into a voltmeter. One of the simplest method to convert a galvanometer into voltmeter is to connect a very large resistance in series, and the whole thing will be used in parallel as a voltmeter in measurement. Therefore, a voltmeter is characterized, a good voltmeter is characterized by large input impedance. So, keeping the input impedance of the voltmeter high is a very important consideration in the design of the voltmeter. If I use transistors for designing my voltmeter, then the input impedance of a transistor, because it is a forward bias junction, is very low. Whereas, if I use in place of the BJT the field effect transistor, the input junction will be a reverse bias junction, and therefore the resistance automatically will be very high, and therefore it will be a much better voltmeter than I design with transistors, BJTs. And therefore, one of the good example of the application of a field effect transistor is a very simple voltmeter made out of FET amplifier. That is what I have been showing to you. Now, what I have what you want to see is, I have a potentiometer here. This potentiometer is actually used for controlling the 0 of the milliammeter. You can adjust the 0 so that the current in this wing is adjusted to make it 0, and this is also used for adjusting the balance of the bridge. And now you apply any external voltage for whatever basic thing that you have, you adjust the 2 potentiometers and make it 0, and then you apply external voltage here. When I apply this voltage is going to be applied as a reverse bias here. So, 1 volt, 2 volt, if I apply here, correspondingly the variation in the resistance will change the balance of the bridge, and therefore there will be a current flow, and if the current flow, if the bridge is properly balanced, the current can become proportional to the voltage. Then I have a very nice electronic voltmeter. Normal galvanometer or a current meter is converted into electronic voltmeter by having a very simple field effect transistor amplifier in the circuit, in the configuration that I have shown here. So, this is what I want to show it to you. I will show a demo of this, and then I will also perhaps discuss some of the important aspects of the field effect transistor, which is in this case metal oxide semiconductor field effect transistor, or the IG FET, which is another variation of the field effect transistor. This is a very important device. Again, almost all of integrated circuits make use of this configuration, where the junction is formed in the normal junction field effect transistor, whereas here what we do, we actually use like this. You have a N channel, you have a P substrate on which you make two regions of N with a gap in between. Over this gap you put a silicon dioxide, an insulator. Silicon dioxide is an insulator, and over that you put a metal. Therefore, you have a metal insulator and a P substrate that forms a capacitor sort of a thing here. So, this N will become the drain, the source, and this will become the drain. So, I have a VDSS here, and all are on the same side of the silicon wafer, and I have an insulation here. Therefore, the gate becomes insulated from the channel, and therefore, it is called insulated gate field effect transistor. And whatever voltage I apply here, for example, if I apply plus voltage here, then the electrons will be attracted towards this positive electrode. Therefore, whatever minority carriers that I have in the P substrate, they will start accumulating here, and so I get a channel of N produced between these two. Then there could be a current flow, and so you get a corresponding field effect transistor brought into operation. So, this is the metal oxide semiconductor field effect transistor, and there is another variation of that. This is called the enhancement mode. There is another method which is called the depletion mode, and these two find very wide application in different areas of electronics, especially in modern electronics. So, now what I would do is I will complete the discussion by showing an actual demo of the FET voltmeter about which I explained to you. So, you can see the circuit diagram here. It is exactly the same as the one which you have just now seen on the screen. You have the field effect transistor in the form of a bridge, Wheatstone's bridge, and this is the voltmeter, current meter connected between these two ends, and this potentiometer and this potentiometer are the one for adjusting the zeros, and you apply the input voltage between the gate and the source of this field effect transistor for operation. Now, I am using this voltage source, which is a very familiar voltage source we have been using all along in these lectures, and this is a millivolt source that is used as the external supply, external voltage. So, I am going to vary the voltage here 1, 2, 3, 4 etc., and see how the deflection is changing in the ammeter that I have here in the circuit. Right, on this side I have a voltmeter, and I also have a current meter. This current meter is the one which I have in the circuit, and this voltmeter is just to measure the voltage that is produced at the input. So, now you see there is no current in the current meter, there is no current in the current meter. So, the potentiometers have been adjusted to become 0. Now, I am going to apply a 1 volt from this power supply. So, this is 1 volt which is applied between the gate and the source, and correspondingly I want you to see what happens at the meter, current meter. You look at the current meter. So, there is a deflection here. So, this is for 1. If I now reduce it, it comes down. If I increase it, it comes for 1 volt. Now, I go to the next position, minus 2 volts. See what happens, the current increases to much larger value. So, if I keep increasing, why is it changing? It is because the gate source voltage is now varied, and therefore, the resistance is changing, and therefore, in the bridge there is an imbalance, and therefore, there is a current flowing through that. So, this is what being made use of as the voltmeter. Now instead of applying 1 volt, I can put a potentiometer here and make it up to 0 to 1 volt. I can reduce this voltage that I apply here to 1 volt when I apply 10 volt. That means I can have 10:1 reduction here. That means this voltmeter will read from 0 to 10 volts. If I make a reduction from 100 to 1 by having number of resistors here, then I can have this voltmeter current meter read up to 100 volts. So that is what normally done in a multimeter. You have different ranges because you have different input attenuators which will proportionally reduce the voltage, and basic voltmeter, this voltmeter will be good for 1 volt or 2 volt for full scale deflection, but by introducing the dividers here I can make it measure higher magnitude of voltages and things like that. So that is how I get a multimeter in principle. Multiple voltages can be selected and then the whole voltmeter can be designed. This will be a very interesting exercise to try to make this work for 0 to 10 volts, 0 to 100 volts and 0 to 1 volt for full scale deflection. You can adjust by adjusting the resistors in the bridge and you can achieve this very easily. So it becomes a high impedance almost ideal voltmeter because I am using a field effect transistor which requires reverse bias at the input, and therefore this is a very good example of an application circuit of the field effect transistor. So in the past few of the lectures you would have seen the whole area of the basic concepts in electronics have been explained in a very practical way. Wherever there is necessary, we also showed an actual demonstration of the different circuits, and then the focus is more on applications of operational amplifier, even though we discussed some aspects of basic diode, transistors, BJT, unijunction transistor, silicon control rectifier and other related devices. But the main focus of these lectures have been on integrated circuit operational amplifier because they are much easier to buy and use, and they are much more closer to an ideal device and therefore much easier to understand in various applications, and it is also very modern. So the lectures will not be complete unless I also tell you some good books for reference. If you are interested in reading more important materials or higher levels of electronics you want to reach, then it is important that you try to get into some very good books written on this topic. There are enormous number of good books are available in the market. Apart from that, in the internet you have enormous number of resources available for learning electronics on your own from the basic level. But I would like to list few of the important books that I have also been following, and I hope you will also have occasion to follow. These are Electronic Devices and Circuits by David A. Bell. This is the 3rd edition by Bell, David A. Bell. This is a very lucid and nice book. And then Principles of Electronics by S. Chand, and Integrated Electronics by Millman and Halkias. This is a very exhaustive book, very well written book and a wonderful textbook. And then the best book I would say is The Principles of Electronics by Albert P. Malvino. It is almost like a novel. You can read it and understand very easily very difficult concepts in electronics. But with lot of simple examples he would have explained the various concepts of the diode, the transistor, the integrated circuits and things like that. What I have not discussed in these lectures is the principles of digital electronics, which by itself is a very important area, and that is the one which is responsible for the modern day computers and things like that, and they are also not very difficult. They can very easily be understood, and if there is an opportunity perhaps we will discuss about the basic digital circuits and fundamentals. Thank you very much.